1,000-ton stone rests in a desert quarry, cut with impossible precision. How did ancient builders move it without cranes or computers? This is the profound enigma we are exploring today. We are about to journey through 20 lost architectural techniques that suggest a material knowledge rivaling our own. You will gain a new perspective on human history, one where the past holds silent lessons for our future. We will see stones fitted tighter than a credit card and metal that refuses to rust after 16 centuries. By the end, you will see these monuments not as ruins, but as unanswered questions. What if the timeline of human ingenuity is not a straight line, but a circle where we are still catching up to forgotten masters? What does a civilization leave behind when its methods vanish? The real mystery is not just how they built these wonders, but why we ever forgot how they did it. Are we ready to admit how much we still have to learn from the ancient world? Our world is built on a clear and steady timeline of progress, a story we tell ourselves of slow, incremental improvement. We see the noisy, powerful machinery of a modern construction site, a symphony of steel and hydraulics, and we assume that everything before it was simpler, more primitive. Yet this assumption shatters when you stand before the silent, immovable weight of a structure like the Great Pyramid. It does not whisper of slow progress, it shouts of a mastered understanding, a fluency with stone and space that seems to have arrived fully formed. This is the heart of what we mean by lost knowledge. It is not merely a forgotten recipe or a misplaced blueprint. It is a complete architectural language, a way of thinking about and manipulating materials that appears to have no clear evolutionary path in the archaeological record. When we speak of advanced material knowledge in this context, we are not talking about magic. We are referring to a sophisticated, perhaps intuitive, grasp of geopolymer chemistry that could create artificial stone, or an understanding of acoustic resonance that shaped entire temples, or a precision in stone cutting that defies the presumed tools of the era. Figures like Graham Hancock have compellingly argued that such anomalies demand a reconsideration of our historical timeline, suggesting the fingerprints of a much older, sophisticated culture. Mainstream archaeology, of course, seeks answers within the framework of known history, pointing to immense skill, time, and social organization. The true mystery lies not in choosing one side over the other, but in sitting with the question itself. How does a civilization achieve such a towering peak of practical knowledge, only for the methods of its construction to vanish so completely from human memory? Were these techniques the hard-won secrets of a culture lost to time, or were they brilliant, isolated flashes of genius that were never successfully written down and passed forward? This foundational puzzle prepares us to look at our first specific technique, one that begins with a single, perfect block. The stones of Sacsayhuamán are not simply stacked, they are woven. Place your hand on the surface of this ancient Inca fortress in Peru, and your fingers will glide across a seamless wall of solid rock. There is no crack to feel, no gap for light to pass through, just an undulating surface of massive andesite blocks that fit together with a precision that defies belief. This is polygonal masonry, and it represents a masterclass in seismic engineering and material knowledge that modern builders still struggle to comprehend. The technique goes far beyond simple cutting. Each stone, some weighing well over 100 tons, was individually shaped into a complex, non-repeating polygon. Imagine a three-dimensional stone puzzle where every single piece is a unique shape, carved to interlock perfectly with its neighbors on all sides. The precision is so exact that engineers who have studied it often cite tolerances within 1/100th of an inch. This was not an aesthetic choice, it was a brilliant solution to a constant threat: earthquakes. The irregular, interlocking joints allow the entire structure to flex and shift during seismic activity, the stones rocking and settling back into place without collapsing. This fortress has withstood centuries of tremors that would reduce modern brick buildings to rubble. The method of achieving such a fit remains one of history's great practical mysteries. No mortar was used, the strength is purely in the geometry. How did they do it? Some researchers suggest a knowledge of plant acids that could temporarily soften the hard andesite for precise shaping, a form of chemical mastery. Others point to legends of lost sonic technology, a way to make stone malleable with sound. The most famous example is the 12-angled stone, a block carved with such impossible complexity that it has become a national symbol. To stand before it is to confront a simple, haunting question. What set of tools, what system of measurement, what blueprint could possibly guide a mason to carve a 100-ton block into a shape that fits 12 other unique stones with a seam thinner than a piece of paper? The silence of those perfectly joined walls speaks louder than any theory. If this is what a civilization could achieve with stone alone, what wonders became possible when they turned their attention to joining metal to stone for eternity? That seamless perfection in Peru finds a distant echo in the sands of Egypt, but on a scale that redefines the word monumental. Before the Great Pyramid was the familiar stepped silhouette we know today, it was something else entirely. For centuries after its completion, it stood not as rough, weathered limestone, but as a colossal, gleaming prism. It was clad from base to peak in an estimated 115,000 blocks of highly polished white Chora limestone, each one cut and fitted with a precision that seems to belong to another age of technology. The ancient Greek historian Herodotus described it as a structure covered in stones that were jointed with such incredible care. When the sun struck it, the pyramid did not merely sit on the landscape, it blazed. It was a man-made mountain of reflected light, visible for miles, a statement of power and knowledge written in pure geometry and shine. The true mystery, however, is not in the grand vision, but in the microscopic detail. How were these casing stones created? The joints between these massive blocks, some weighing 15 tons, were reportedly so precise that a credit card cannot slide into the gap. They were not just tight, they were optically perfect, rendered invisible from even a short distance, creating the illusion of a single, impossibly smooth sloping plane. Modern researchers like Christopher Dunn have studied the few remaining casing stones at the base and noted surfaces that are flawlessly flat and corners that are perfectly square, with a precision that suggests machining, not hand chiseling. This has led to profound questions about the tools that could achieve this. Were they using diamond-tipped saws, a technology we do not attribute to the Old Kingdom? Or perhaps a lost polishing method involving a slurry of quartz, sand, and water, applied with such consistent pressure and motion that it created a near-optical finish. Another compelling theory, proposed by materials scientist Joseph Davidovitz, is the geopolymer idea that the casing stones were not quarried at all, but cast in place using a form of advanced ancient concrete, a liquid stone that could be poured into molds to achieve that seamless fit. Each theory grapples with the same evidence, a level of finish and alignment that should not exist alongside copper chisels and stone hammers. The few survivors of that original skin, now clustered at the pyramid's foot, are like fragments of a lost user manual. To touch their still glassy surface is to touch the ghost of the pyramid's original intent, a perfect geometric form sheathed in a mirror. If they could bind stone to stone with such invisible perfection, it forces us to ask what other, even more versatile substances they might have mastered to make their world literally hold together. The ghost of that mirrored pyramid is a testament to stone, but what about a material that could be poured, shaped, and made to defy the sea itself? Step inside the Pantheon in Rome and look up. Your eye is drawn not to a ceiling but to a sky, a perfect hemisphere of ancient concrete that has hung, unsupported, over the heads of visitors for nearly 2,000 years. This is not a metaphor for endurance, it is the physical fact of Roman concrete, a material so advanced that its full recipe vanished into history for over a millennium. Modern engineers call their material concrete, but the Roman version, opus cementitium, was something entirely different. Our concrete has a lifespan, a countdown clock where exposure to elements, especially salt water, begins a process of deterioration. Roman concrete performed a kind of architectural alchemy. It actually grew stronger when immersed in the sea. The secret was in its volcanic recipe. While modern Portland cement relies on heating limestone and clay, the Romans mixed lime with a specific volcanic ash called pozzolana, along with chunks of brick and rock. For centuries, this was seen as a crude, if effective, formula. Then, materials scientists at places like the University of California, Berkeley, put samples under advanced microscopes. What they found rewrote the story. When seawater seeped into the Roman concrete, it did not cause damage. Instead, it triggered a slow, centuries-long chemical reaction. The water interacted with the pozzolana and lime to grow rare, plate-like minerals such as altobermorite throughout the material. These crystals acted as a reinforcing scaffold, blocking cracks and actually strengthening the matrix from within. The Romans themselves may not have understood the atomic-level chemistry, but their empirical mastery was absolute. Look at the Pantheon's dome itself, a marvel of practical genius. They did not simply pour a solid mass of heavy material. They layered the aggregate, using lighter, porous stones like pumice at the top to drastically reduce weight and stress, while maintaining the dome's structural integrity. For a maritime example, one need only look to the ancient harbor of Caesarea. Built by Herod the Great, its concrete breakwaters have been submerged in the aggressive saltwater of the Mediterranean for 2,000 years. Waves that would have reduced a modern counterpart to crumbling rubble in decades have left these Roman structures largely intact, still resting on the seafloor. This forces a profound and practical question. If we could fully rediscover and adapt this self-healing, seawater-loving formula today, how would it transform our world? Imagine coastal cities, seawalls, and bridges built not for a century, but for a millennium, defying the rising seas with a technology pulled from the past. The Romans built for eternity in poured stone. But what about a civilization that sought to create eternity in a single, untarnished piece of metal? The Pantheon's dome stands as a testament to poured stone, but what about a civilization that mastered solid metal to defy time itself? In the heart of Delhi's Quad complex, a 7-meter-tall iron pillar has been standing in the open air, completely exposed to monsoon rains and scorching sun for over 1,600 years. It should be a crumbling relic of rust, yet its surface remains smooth with only a faint, stable patina. This is not luck, it is a metallurgical message from the past, a deliberate demonstration of an alloy science we thought was modern. The pillar, commissioned by King Chandragupta II in the 4th century, is a single, forged piece of pure wrought iron weighing over 6 tons. Forging something of that size and purity with the furnace technology of the era is a staggering feat in itself, but its true secret is invisible, locked in its atomic composition. Modern metallurgists who have analyzed the pillar discovered its recipe, a formula lost for centuries. It contains a very high phosphorus content and unusually low amounts of sulfur and manganese. This specific cocktail is the key. When exposed to air and moisture, the high phosphorus iron does not form the flaky, destructive rust we see on modern steel. Instead, it encourages the growth of a thin, uniform, and protective film called mesawite, a passive layer that actually shields the metal beneath from further corrosion. This is not a random outcome, it is the signature of advanced, deliberate knowledge. The ancient Indian ironsmiths, likely through generations of empirical experimentation, understood how to source the right ores and control their bloomery furnace processes to produce this self-protecting alloy. The pillar's Sanskrit inscription praises the king's victories, but its true boast is in its silent, uncorroded endurance. It stands as a cultural symbol of imperishable strength, a literal iron will that has witnessed empires rise and fall around it. This presents a fascinating historical puzzle. Why was this sophisticated technique not replicated and spread? Was it a guarded guild secret that died with its masters, or was the specific ore source so unique it could not be easily copied? To forge and raise such a colossal iron column speaks to an industrial capability that staggers the mind. It makes you wonder if they could move and erect 6 tons of refined metal with such precision. What other impossible weights were they capable of transporting? This question leads us from the enduring strength of iron to the sheer, incomprehensible mass of stone that defines our next mystery. 16 centuries of iron stand defiant, yet its 6-ton weight is dwarfed by a different kind of megalithic ambition. In the Bekaa Valley of Lebanon, the Roman temple complex of Baalbek rests upon a foundation that predates it by millennia, a platform of stones so large they seem to defy the very laws of physics. Here, the so-called trilithon, 3 perfectly fitted blocks, each weighing approximately 800 tons, form a single course of the wall. To stand beneath them is to feel a profound, humbling sense of scale, a visceral understanding that the people who placed them there operated on a different logistical plane. Yet even these are not the champions. Just a short distance away in the quarry lies the true behemoth, the stone of the pregnant woman, a single block of limestone estimated to weigh over 1,000 tons. It is the largest known worked stone from antiquity, still partially attached to the bedrock, as if the builders simply walked away from a task that even they found insurmountable. The question is not just how they cut it, but how they ever intended to move it over half a mile to the temple site. The engineering challenges are almost paralyzing to consider. The friction alone, the sheer ground pressure of a 1,000-ton block on any kind of sled or rollers, would have crushed the roadway beneath it into powder. The manpower required, using only ropes, wood, and levers, reaches into the tens of thousands, requiring a coordination of effort that seems more myth than history. Mainstream archaeology, represented by experts like Jean-Pierre Adam, proposes immense but conventional methods, a symphony of wooden rollers, levering stations, and teams of oxen, combined with a ramp system that would have been a colossal earthwork project in itself. They point to the clear evidence of levering points and sled tracks found on similar, smaller stones. Yet the scale at Baalbek pushes these conventional explanations to their absolute limit. This has led to more speculative ideas, whispered in the same breath as the sonic softening of stone, or even a form of acoustic levitation, where vibrations could temporarily reduce friction or the effective weight of the block. While these remain firmly in the realm of theory, they speak to the depth of the mystery. For a modern perspective, consider the story of the Thunder Stone in St. Petersburg, a roughly 600-ton granite block moved in the 1760s with the aid of advanced metallurgy, custom bronze rollers, and a small army of workers. It was hailed as a triumph of modern engineering. The builders of Baalbek aimed to move a stone nearly twice that mass over rougher terrain with only bronze and wood. The gap in capability is staggering. From the moai of Easter Island, rocked into place over miles, to the multi-hundred-ton blocks at Ollantaytambo in Peru, cultures worldwide faced this same megalithic puzzle. Baalbek simply presents it in its most extreme, most breathtaking form. It forces a logistical question that bridges quarry and construction site. Once you have moved a mountain, how do you then shape it with the delicacy of a jeweler? The sheer mass of Baalbek stones speaks of raw power, but the true signature of a lost technology is often found in the smallest, most telling details. Take a long, cylindrical core of granite drilled from deep within an Egyptian quarry. On its surface, you will not find the jagged, chipped marks of a pounding copper tool. Instead, you see a perfect, continuous spiral groove winding around the stone like the thread of a giant screw. This groove is smooth, uniform, and deep, and it tells a story that conventional Egyptology struggles to narrate. It is the unmistakable fingerprint of a drill bit that did not merely scrape, but penetrated solid granite with a speed and pressure that feels shockingly modern. Engineers who have examined these cores, like Christopher Dunn, point to the geometry of the groove itself. The spacing between each spiral turn is remarkably consistent and wide, indicating the drill advanced into the incredibly hard stone at a rate of inches per revolution. To achieve this, the tool would have needed to spin at a high speed while simultaneously bearing down with a feed pressure of several tons. This is not the work of a man turning a copper tube with sand. This is the performance profile of a machine. The mystery deepens when we look at the saw cuts in other granite artifacts. Sarcophagi and boxes show long, straight curves that are perfectly parallel and smooth, again suggesting a saw blade of immense stability and power, one that could slice through granite as if it were soft wood. So what tool could have done this? The mainstream theory involves a tubular copper drill rotated by a bow, using a slurry of quartz, sand, and water as the abrasive. While this can work, experiments show it produces a rough, uneven core with a much narrower groove spacing, a far cry from the clean, deep spirals on the ancient samples. This has led to more speculative yet fascinating proposals. One is the concept of ultrasonic machining, where a tool vibrates at an extremely high frequency, effectively pulverizing the stone at a microscopic level to allow for smooth, precise cuts. Another, even more compelling idea is that the drills themselves were tipped with something harder than copper, perhaps jewels or even manufactured diamonds, mounted in a way that allowed for sustained, heavy-duty work. Look at the precision box holes found at sites like the Serapeum of Saqqara, where rectangular cavities are cut into solid granite with sharp, perfect corners, a feat nearly impossible with simple abrasives alone. Or consider the unfinished obelisk in Aswan, a monument abandoned in the bedrock that shows clear evidence of trenching work around its perimeter. The scale and precision of these work sites suggest an industrial process, not just artisan craft. This evidence forces a practical, almost uncomfortable question. Does the presence of such advanced machining marks point to a source of mechanical power we have not yet considered for that era? Could it have been a large, geared apparatus driven by water or even animals on a treadmill, providing the consistent torque and downforce needed? Or does it hint at a material science that gave them cutting tools far superior to the basic copper we find in their tombs? The spiral groove in that granite core is a silent scream of a lost capability. It suggests that when ancient builders faced the hardest stones on Earth, they did not struggle, they mastered them. But what if the ultimate mastery was not in cutting stone, but in convincing it to behave as if it were something else entirely? The spiral groove in that granite core is a silent scream of a lost capability. Yet in the high plains of Bolivia, at a site called Pumapunku, the stones themselves seem to cry out in a language of shattered geometry. You are not looking at a finished building, but at a sprawling, apocalyptic workshop. The ground is littered with hundreds of massive andesite blocks, each one cut with a precision so sharp, so clean, it looks as if it came from a modern machine shop. These are not simple blocks, they are intricate components featuring perfect right angles, razor-sharp edges, and complex geometric channels and notches that interlock with mathematical certainty. Some have precise H-shaped recesses, as if designed to hold metal clamps, a modular construction system that feels eerily contemporary. The andesite here is notoriously hard, a challenge for even modern diamond-tipped tools. So how did a culture without the wheel or written language achieve this? One of the most persistent and controversial theories points not to harder tools, but to a method of making the stone itself temporarily soft. Indigenous legends recorded by early Spanish chroniclers speak of a plant whose juices could melt stone, allowing it to be molded like clay. Early 20th century explorers reported hearing similar tales from local guides about a liquid that ate stone. This has fueled the idea of a lost chemical knowledge, a plant-based agent, perhaps containing high levels of oxalic acid found in local vegetation, that could etch or soften the andesite surface for precise shaping. Modern experiments have shown that oxalic acid can indeed create visible marks on stone over time, lending a sliver of plausibility to the old stories. Could the builders have applied a poultice of these plants, letting the chemistry do the work before finishing the surface with grinding? Mainstream archaeology, however, presents a different, equally staggering picture of human effort. Experts like archaeologist Alexei Vranish argue that all this work was accomplished through the immensely laborious process of pecking and grinding. Using hammerstones of even harder rock, a worker would have patiently bruised the surface of the andesite, grain by grain, then used sand and water to grind it smooth over months or years. They point to unfinished blocks that show this very pitted texture. The precision in this view is a testament not to lost chemistry, but to almost unimaginable patience, skill, and generations of dedicated labor. So, which narrative feels more complete? Do you see the scattered puzzle pieces of Pumapunku as the debris of a workshop where masters used a forgotten material science to shape stone like putty? Or do you see a monument to sheer human will, where every flawless channel and perfect right angle was won from the rock through millions of deliberate strikes? This site forces a choice between two profound ideas of the past, one of chemical mastery and one of monumental perseverance. Yet if such effort or knowledge was expended to shape individual stones, it implies a purpose far greater than the components themselves. It suggests each piece was destined for a grand design, one that may have reached not just across the earth, but was intended to mirror the heavens above. Inside Newgrange, darkness is not an absence but a waiting presence. For 51 weeks of the year, the inner chamber of this 5,000-year-old passage tomb in Ireland rests in profound silence and shadow, a stone womb buried beneath a mound of earth and white quartz. Then, for a few precious minutes around the winter solstice, something miraculous happens. As the sun crests the distant horizon, a slender beam of golden light pierces a specially constructed opening above the entrance, known as the roof box. It travels down the long, narrow passageway, a corridor of precisely placed stones, and finally floods the central chamber with a radiant glow, illuminating spiral carvings that have not seen daylight for a full year. This is not a happy accident of architecture. It is a deliberate, breathtaking feat of Neolithic engineering that required an advanced knowledge of astronomy, geometry, and the unwavering cycles of the cosmos. To achieve this, the builders had to orient the entire 62-foot passage with pinpoint accuracy to align with the rising sun on the shortest day of the year, a calculation that required generations of observing the sky and marking the sun's slow, yearly dance. The structure itself is a marvel of practical design, featuring a corbelled roof that has remained completely watertight for millennia, and a brilliant white facade of quartz cobbles that would have caught the first light of dawn and made the entire mound appear to glow from within. But the sophistication of Newgrange extends beyond light into the realm of sound. Researchers in the field of archaeoacoustics, like those at the University of Salford, have studied similar Neolithic sites and discovered that their chambers are not silent. They possess remarkable acoustic properties, certain resonant frequencies that can amplify sound, create echoes, or even induce altered states of consciousness. The very shape and materials of the stone chambers were likely chosen to manipulate sound waves, turning ritual chants or drumbeats into immersive, otherworldly experiences. This suggests a holistic design philosophy where the architecture was engineered to engage multiple human senses simultaneously, to harmonize with the environment on a profound level. The builders understood that a sacred space was not just a visual spectacle, but an auditory and celestial instrument. They synchronized stone with sunrise and shaped chambers to hold sound, demonstrating an intuitive grasp of environmental physics that we are only now beginning to measure. This deep connection between structure, cosmos, and human perception reveals a mind that saw building not as separate from the natural world, but as a way to converse with it. If a culture could orchestrate light and sound with such intention, it makes their approach to the raw material itself, the single, unbroken piece of stone, all the more significant. The architects of Newgrange worked with light and shadow, but in the caves of Ellora they confronted the mountain itself. Here, the Kailasa temple stands not as a structure assembled from quarried stone, but as a mountain that was meticulously unmade. This is the ninth lost technique, the staggering art of monolithic rock-cut architecture. Unlike any temple built from the ground up, Kailasa was envisioned in reverse. Master planners stood before a solid, living cliff of basalt and saw the finished form hidden within it. Their task was not to add, but to subtract, to carefully remove over 200,000 tons of rock with the precision of a sculptor revealing a statue from a block of marble, but on a scale that defies comprehension. This vertical excavation is a lost art of planning and execution, a high-stakes operation where a single miscalculation could have led to a catastrophic collapse of the entire vision. It required a profound, almost intuitive knowledge of the rock itself, understanding its natural strata, internal stress points, and weaknesses. Before the first chisel ever struck, the entire three-dimensional plan of the multi-story temple, with its pillared halls, intricate galleries, and soaring ceremonial spire, had to be locked in the minds of the master architects. They began by carving deep, open trenches down from the top of the cliff, isolating a gigantic block of stone that would become the central temple body. Then, for generations, teams of sculptors and laborers worked from the top down, using iron chisels and hammers to carve not just the outer shape, but the interior spaces as well. They hollowed out the grand audience hall, chiseled life-size elephants that appeared to be carrying the temple on their backs, and created elaborate friezes telling epic stories, all from the living rock. Every pillar, every statue, every decorative motif was carved in situ, meaning it was never separate from the mountain. It was always a part of it, revealed by removal. The scale of the manpower and timeline is staggering, likely involving thousands of workers over multiple reigns in the 8th century. This achievement stands as the ultimate testament to what dedicated, organized human craftsmanship can accomplish with a unified vision and relentless effort. Yet, it still leaves a quiet question lingering in the dust-filled courtyards. While we know the basic tools, could there have been a lost method for the initial, massive excavation? A way to split and remove such vast quantities of basalt more efficiently than we suppose? The temple's existence is a monument to subtraction, to the power of removing everything that is not the sacred form. This act of revealing a single, unified whole from a mountain finds a strange parallel in a different technique, one that also seeks perfect unity, but by joining many separate pieces into a single, seamless skin. The silent strength of a mountain carved into a temple finds its echo in the quiet, intricate logic of a wooden joint. Within the shadowed halls of a centuries-old Japanese temple, you will find no roar of stone being cut, but a different kind of precision, one of whispered grain and perfect embrace. Here, colossal timber frames soar overhead, holding up immense tiled roofs through typhoons and tremors for over 1,000 years, yet they are assembled without a single nail, screw, or metal fastener of any kind. This is the 10th lost technique, the art of Kigumi, or traditional Japanese wood joinery, and it represents an advanced, almost philosophical knowledge of wood as a living, breathing material. The master carpenter does not force wood into submission. He converses with it, understanding its personality, its memory of being a tree, and how it will move with the seasons and the shaking earth. This empirical science of organic material is passed down not through textbooks, but through decades of apprenticeship, a lineage of tactile knowledge where the secrets of a joint are as guarded as any alchemical formula. Consider a joint with a name like a poem, the Shiho Koshike Kakashi Ari, a hidden four-way shoulder joint. From the outside, the meeting of two beams appears perfectly seamless, a simple intersection. But inside, the ends of the timbers are carved into a complex three-dimensional puzzle, with interlocking shoulders, wedges, and sockets that lock together under pressure, actually becoming tighter when weight is applied from above. This is not just carpentry, it is dynamic engineering in wood. Each joint is designed with a specific purpose, some to allow for controlled movement during an earthquake, letting the structure sway and settle without breaking, others to counteract wood's natural tendency to shrink and warp across the grain over centuries. The selection and preparation of the wood itself is a lost science. Master builders would choose specific trees, often Japanese cypress or cedar, for their straight grain and natural resins, then season them for years, sometimes decades, in precise conditions to stabilize the material before a single cut was made. They understood moisture content, grain direction, and seasonal movement on a level that modern kiln drying often struggles to replicate. This broadens our entire definition of ancient material knowledge. It was not limited to inert stone or smelted metal, but extended to a profound, symbiotic relationship with organic materials. They did not see wood as a dead commodity, but as a partner with its own rules, and by mastering those rules through observation and refinement over generations, they created frameworks that outlast empires. This deep respect for a material's inherent behavior, this intention to build in harmony with natural forces rather than simply overpower them, leads to a compelling question. If they could design wood to dance with earthquakes, what other elemental challenges did they learn to face, not with brute force, but with clever, enduring solutions? The ancient builders of Teotihuacan did not just see their city as a collection of structures, but as a single, living entity that needed to breathe. Along the vast avenue of the dead, under the watchful gaze of the Pyramid of the Sun, every surface once gleamed with a brilliant, almost blinding coat of white lime plaster. This was far more than a simple aesthetic choice, a desire for a clean, uniform look. This was the 11th lost technique, a self-cleaning and potentially air-purifying stucco that transformed the city's skin into an active, intelligent interface with the environment. Modern analysis of samples from these ancient facades has revealed a secret ingredient: micaceous minerals. When mixed into the lime plaster, these tiny, plate-like particles created a surface that was hydrophilic, meaning it attracted water. When rain fell, it did not bead up and drip slowly, allowing dirt to accumulate. Instead, it sheeted off in a continuous, cleansing film, washing dust and grime from the walls and leaving them looking perpetually fresh and luminous. The process of making this plaster was itself a chemical marvel. Workers would burn limestone in kilns to produce quicklime, a caustic powder. This was then slaked with water, undergoing a violent reaction to become lime putty, which was mixed with aggregates like sand and, crucially, these specific crushed minerals. But the sophistication may have gone even deeper. Some researchers, analyzing the composition, have suggested the possible inclusion of natural zeolites, volcanic minerals with a microporous structure. Zeolites are known in modern times for their ability to trap and neutralize pollutants, acting as molecular sieves. If intentionally added, it implies the Teotihuacanos engineered their building surfaces not just to clean themselves, but to passively purify the very air around them, breaking down organic compounds or absorbing odors. This represents an applied, almost instinctual knowledge of nanotechnology and environmental chemistry centuries before the terms existed. They were creating a smart material, a building skin that interacted dynamically with sunlight, rain, and atmosphere. The pyramid of the sun, coated in this miraculous plaster, would have functioned as a gigantic environmental regulator, a white beacon that cleaned itself with every storm and perhaps even improved the quality of the air at its base. This forces us to look at all ancient finishes with new eyes. How many other smart materials have we overlooked, scrubbing away as simple paint or plaster? If they could engineer walls to interact with the weather, it makes you wonder what other daily necessities they reimagined with similar ingenuity. How, for instance, did they push back the darkness inside their pristine, self-cleaning halls? The mystery of illumination awaits. Deep within the painted corridors of Seti, the first tomb, the air holds a secret as profound as the artwork on the walls. In this sprawling underground complex, one of the largest and most ornate in the Valley of the Kings, you will search in vain for the one thing that should be everywhere: the black, greasy soot from torches or oil lamps. The ceilings and upper walls, adorned with millions of intricate hieroglyphs and vibrant scenes of gods and the afterlife, are pristine. This absence presents a brilliant practical puzzle. How did teams of artists work for years in these windowless, twisting passages hundreds of feet into a hillside without leaving a single mark of their own illumination? The conventional image of workers holding flickering, smoky torches simply does not fit the evidence here. This points to a 12th lost technique, a sophisticated and possibly lost method of clean, powerful subsurface lighting. One compelling theory involves the strategic use of polished metal mirrors, likely made of a copper alloy called speculum, which could produce a highly reflective surface. Engineers and historians have modeled how a carefully arranged relay of such mirrors, stationed at corridor intersections and perhaps even in shafts dug for the purpose, could have channeled beams of sunlight deep into the tomb's interior. This would have provided a bright, steady, and completely smokeless light source for the master artists, allowing them to see fine details and maintain consistent colors without contaminating their own masterpiece with smoke. Another possibility lies in the use of advanced oil lamps with specially designed wicks and perhaps purer fuels, like refined sesame or castor oil, that could burn with a remarkably bright and clean flame. There are even intriguing, though less substantiated, suggestions of using bioluminescent materials, like certain fungi or prepared jars of glowing chemicals, mentioned in vague terms in some later texts. The practical challenges of any of these methods are immense. Maintaining the precise angles of a mirror relay as the sun moved across the sky would have required constant adjustment by a dedicated team. Creating a fuel that burned without significant residue would imply a refined knowledge of chemistry. This mystery is not unique to Egypt. In the elaborate underground cities of Cappadocia, or within the dark chambers of Newgrange we discussed earlier, we find similar puzzles of how complex work was accomplished far from the sun. The lack of soot in Seti's tomb is a silent testament to a forgotten workplace technology. It forces us to reimagine those sacred spaces not as gloomy crypts, but as well-lit studios where light itself was a mastered tool. This mastery of the interior environment, of creating ideal conditions for human artistry deep within the earth, reflects a planning mentality that looked beyond the single room or even the single building. It suggests a mind capable of orchestrating light, labor, and logistics on a scale that would soon be applied to an entire city, designed from the ground up with a cosmic blueprint. The pristine walls of an Egyptian tomb speak of mastered light, but an entire city designed to master water reveals a different kind of genius. In the arid plains of the Indus Valley, over 4,000 years ago, the citizens of Mohenjo-Daro walked on baked brick streets laid out in a perfect grid, their waste carried away by a network of covered drains, their water drawn from deep, brick-lined wells. This was not a haphazard settlement. It was a meticulously engineered machine for living, a testament to the 13th lost technique, large-scale civil engineering rooted in hydraulic mastery and systematic urban planning. The knowledge here was not about moving mountains, but about managing the mundane on a civic scale with a foresight that feels strikingly modern. Every aspect of the city's layout reveals a central, governing intelligence. The main streets ran north-south and east-west, dividing the city into large blocks with smaller lanes branching off to individual homes. This grid was not for aesthetic symmetry. It was for efficiency, airflow, and most importantly, for the flow of water and waste. Beneath those orderly streets ran the city's true lifeline and its most brilliant innovation, a sophisticated drainage system. Each house had its own bathing area and latrine, with waste channels that fed into larger, street-side drains covered with carefully fitted brick slabs. These drains were sloped to ensure gravity-driven flow and featured inspection holes for maintenance, a clear sign of long-term planning. The engineering extended to waterproofing. Archaeologists have found evidence that the Great Bath, a large public reservoir at the city's heart, was made watertight with a layer of bitumen, a natural tar, set between finely fitted bricks and an outer wall of clay. This indicates a practical knowledge of chemistry and material properties, using locally available resources to solve a critical problem. The uniformity of the bricks themselves is another silent marvel. Millions of them, all fired to a consistent standard in ratios of 4:2:1, suggest a centralized, almost industrial production with quality control. This standardization meant every brick was interchangeable, speeding construction and ensuring structural reliability. The city's relationship with water was proactive, not reactive. A network of wells, built with special wedge-shaped bricks to form a circular shaft, tapped consistently into the freshwater table, providing a reliable supply even as the nearby river shifted its course. The entire city was also built on massive mud brick and clay platforms, raising it above the floodplain of the Indus River. This was urban planning as applied public health. By managing sanitation and clean water with such systematic rigor, Mohenjo-Daro likely enjoyed a level of community health and longevity that many later cities would struggle to match for centuries. The profound mystery is not in how they built it, but in how this comprehensive, systematic knowledge of city building seems to have fragmented and faded. The Indus Valley script remains undeciphered, and with it, perhaps the official manuals of their civic engineers. The city stands as a ghost of a perfectly logical, orderly world, a blueprint for urban life that was somehow misplaced by history. It represents the peak of applied, collective knowledge for the betterment of daily life. Yet, this very orderliness makes the next chapter of our story so compelling. For when we look to the Americas, we find evidence of a different kind of large-scale engineering, one that traded straight lines for vast, mysterious shapes etched into the landscape itself, moving from the logic of the city to the enigma of the earth. The orderly grid of Mohenjo-Daro is a map of human logic, but in the high desert of Peru, the land itself becomes the canvas for a message written on a scale only the sky can read. From the ground, the Nazca Desert is a monotonous plain of dark, sun-baked pebbles, but ascend to the vantage of a hill or a low-flying plain, and the landscape transforms. Here, etched across hundreds of square miles, are colossal geometric shapes, perfect triangles and trapezoids, and intricate depictions of animals, a hummingbird with a beak longer than a football field, a spider, a monkey with a spiraling tail. These are the Nazca lines, and their creation represents a 14th lost technique, a profound geotechnical knowledge of the desert itself as a building material. The method seems deceptively simple. The ancient Nazca people between 2,000 and 1,500 years ago did not build up, they scraped away. They carefully removed the top layer of dark, iron oxide-coated pebbles, the desert pavement that naturally forms over centuries, to reveal the lighter, creamy-colored subsoil beneath. This created a stark visual contrast that has endured for millennia. The true lost knowledge, however, lies in the sophisticated understanding this process required. They were not just making scratches in the dirt, they were performing a kind of large-scale soil surgery. They had to comprehend how the desert patina forms and how to remove it without triggering catastrophic erosion. They knew that the exposed subsoil, a mixture of sand, clay, and calcium, would harden into a durable crust when exposed to the sun and the occasional mist from the Pacific, locking the designs in place against the fierce, scouring winds. This reveals a deep, empirical mastery of local geology and microclimate. The surveying challenge is perhaps the greatest puzzle. How do you map a perfect straight line that runs for over 5 miles across broken terrain, or outline a complex biomorphic figure without the ability to see your work from above? The mainstream and most plausible explanation involves remarkable, yet low-tech precision. Archaeologists like Joinery of the University of Kentucky have demonstrated that using simple wooden stakes and lengths of cord, teams could have transferred scaled-down designs from small models to the giant desert canvas using geometric principles, creating straight lines by sighting between stakes and curves by using a central pivot point and a rope. This showcases the power of organized human effort and basic mathematics. Yet the sheer scale and the perfect proportionality of the figures, maintained over uneven ground, still inspires awe and alternative speculation. Some researchers have wondered if the Nazca possessed large, tethered balloons or kites for aerial supervision, a theory that, while unproven, speaks to the depth of the mystery. The purpose of the lines remains debated, likely tied to ritual, astronomy, or water deities in the arid landscape, but their legacy as an engineering feat is clear. The Nazca people did not quarry stone or pour concrete. They manipulated the very skin of the earth. They understood their materials so intimately that they could create art on a geographic scale that would persist for centuries by using the desert's own natural processes to their advantage. This act of working with the landscape, of using subtraction to create a lasting impression, hints at a mindset that saw the environment as an integrated partner. It makes you wonder if they could command the desert floor with such precision. What other elemental forces did they learn to harness, perhaps even capturing and concentrating something as intangible as light itself within the very stones they shaped? The desert floor became a canvas for the Nazca, but in the shadowed depths of an Egyptian monument, the stone itself seems to hold a captured light. Beneath the sands of Abydos, adjacent to the temple of Seti I, lies the Osirian, a haunting and enigmatic structure. It is a stark contrast to the ornate temples above, built from colossal blocks of red granite in a stark, minimalist style that feels impossibly ancient. Its central hall is a sunken island surrounded by a channel of water, framed by 10 monolithic pillars, each a single piece of stone weighing tens of tons. The atmosphere here is one of immense, silent weight, a feeling of being in the presence of something built not for the living but for eternity. Within this somber space, a peculiar detail has fueled decades of speculation. Some researchers and visitors have reported finding large, naturally formed crystals, primarily clear quartz, embedded within the very fabric of the granite blocks themselves. This is not about decorative inlays, but the idea that the builders intentionally selected stone containing these crystalline structures during quarrying. Why would they go to such extraordinary effort? One compelling, though highly debated, theory suggests this was a deliberate application of a lost material science. Quartz is a piezoelectric material, meaning it can generate a small electrical charge under mechanical stress, such as the subtle vibrations of the earth or even sound waves. If the builders understood this property on an empirical level, they may have been using these crystal-laden stones to harness or amplify subtle energies within the sacred space, perhaps to enhance acoustic resonance during rituals or to create a specific ambient environment. The concept bridges the gap between advanced physics and what we might call esoteric architecture. It proposes that material selection was guided not just by strength and appearance, but by a hidden functionality, a vibrational quality. Mainstream Egyptology offers a more grounded explanation. The red granite for the Osirian was quarried at Aswan, a region known for its granite that can naturally contain veins and pockets of quartz and other minerals as it cooled from magma millennia ago. In this view, the crystals are a geological coincidence, not an intentional feature. The builders simply used the finest, most massive blocks they could extract, and the quartz came along with it. The debate itself is illuminating. It forces us to ask how we interpret intention in the ancient world. Were the builders sophisticated geologists who understood crystalline properties, or were they master craftsmen who simply sensed, on an intuitive level, that certain stones felt more appropriate, more alive, for a monument dedicated to cycles of renewal? The Osirian, whether by design or profound coincidence, stands as a testament to stone chosen for more than its durability. It suggests a worldview where the boundary between the physical and the energetic was fluid, where a building's power could be woven into its very substance. If the choice of stone could be influenced by such subtle, celestial principles, it is a logical step to structures built with the grandest celestial clock in mind, turning entire mountains into observatories. A monument to the sun and moon was not built with glass and gears, but with stone and shadow. Stonehenge stands on the Salisbury Plain not as a primitive circle, but as a sophisticated astronomical machine, a 16th lost technique of encoding celestial knowledge into the very bones of the earth. Its builders were not merely stacking rocks, they were programming a calendar, using the immense, shaped sarsen stones to capture the most dramatic moments of the solar and lunar cycles. The most famous alignment is the midsummer sunrise, where the first light of the longest day crests the horizon and shoots directly through the heart of the monument, framed by the great central archway. But the sophistication runs far deeper. Other stones and sightlines are thought to mark the winter solstice sunset, and even more complex lunar alignments, tracking the moon's 18.6-year cycle of extremes, a pattern that could predict eclipses. This was long-term cyclical knowledge made permanent, a way to anchor the fleeting movements of the sky into the unmovable certainty of stone, ensuring that generations to come would know when to plant, when to celebrate, and when to witness the cosmos turning. The method of creating this stone computer reveals a mastery of material and form. The massive sarsen stones, a uniquely hard sandstone, were shaped with a patience that defies modern haste. Using only stone mauls, heavy hammerstones of even harder rock, workers patiently pounded and ground the surfaces over countless hours, likely employing a technique of heating the stone with fire and then rapidly cooling it with water to induce controlled flaking. Each upright was carefully dressed, its sides subtly tapered and curved to account for perspective, creating the illusion of straight, parallel columns when viewed from the ground. Then came the woodworking principle applied to geology, the mortise and tenon joint. On top of each upright, they carved two protruding knobs, the tenons. On the underside of the massive lintel stones that span the tops, they carved corresponding hollows, the mortises. These were not crude fits, they were precision carved so that when lowered into place, the lintels locked onto the uprights, creating a stable, interlocking ring that has withstood millennia of wind and weather. This shows a mind that could see stone not as a dead weight, but as a material that could be joined with the same logic as timber. Perhaps the most telling clue to their material knowledge lies in the smaller, inner circle of bluestones. Geological analysis proves these distinctive spotted dolerite stones were transported over 150 miles from the Preseli Hills in Wales. This was not a casual choice. Moving 80 or more stones, each weighing up to 4 tons, across rivers, valleys, and rough terrain, represents a logistical obsession that speaks to a powerful motive. The leading theory suggests these particular stones were chosen not just for their color, but for their perceived properties, perhaps linked to healing or spiritual significance, a value placed on specific geology that we can no longer fully comprehend. The heel stone, that solitary sentinel outside the circle, stands as the final piece of the alignment puzzle, the foresight that catches the first golden sliver of the solstice sun. Stonehenge, therefore, is a triple masterpiece, a fusion of astronomy, engineering, and a profound, almost sacred, understanding of material provenance. It demonstrates that the ultimate goal was not just to build something that would last, but to build something that would speak, to track time itself across centuries. This pursuit of perfect alignment with cosmic forces required an equally perfect foundation, a stage that was flawlessly level, leading to an obsession with the one thing that seems most mundane, the creation of a perfectly flat surface. That celestial calendar carved from stone required a foundation of absolute precision, a stage perfectly level for the dance of light and shadow. This obsession with flatness finds its most bewildering expression not in vast monuments, but in small, enigmatic objects. Scattered through museum collections are ancient artifacts, like the controversial clay jars from Iraq, sometimes called the Baghdad Battery, or certain Egyptian stone boxes, whose surfaces present a silent, microscopic challenge. When analyzed with modern precision instruments, these surfaces are not merely smooth to the touch, they are optically flat. This means that across their entire plane, they deviate by less than 1/1000th of an inch, a tolerance so tight that light reflects off them in a perfect, unbroken wave without distortion. Achieving this is not a matter of skilled hand sanding. It is the domain of advanced lapping and polishing, a 17th lost technique that hints at a workshop standard we never knew existed. To create an optically flat surface, you cannot trust your eye or hand alone. You need a reference surface of known perfection, called a master flat. The ancient artisan would have needed to create at least 3 such master surfaces, painstakingly rubbing them together in pairs with a fine abrasive slurry, a paste of crushed garnet or corundum in oil or water. By rotating and crossing the strokes in a precise method, high spots are gradually worn down until all 3 surfaces match each other perfectly, a process that can take hundreds of hours. Only then could they use one master to lap and perfect a workpiece. This implies not just patience, but a systematic, repeatable industrial process and a means of measurement far beyond a simple ruler. Precision engineers and metrologists who have examined artifacts like the granite coffer in the King's Chamber of the Great Pyramid have noted this same startling flatness on interior surfaces, alongside corners that are perfect right angles to within a fraction of a degree. The coffer, carved from a single block of solid granite, has walls and base so flat and parallel they could serve as a reference surface in a modern machine shop. The question this forces upon us is not how, but why. What possible purpose did such extravagant, invisible perfection serve in a stone box sealed inside a pyramid or on the surface of a simple clay jar? For a sealing function, ordinary smoothness would suffice. For aesthetic reasons, no one could see the difference. This level of precision only makes sense if it served a mechanical or functional need we no longer understand, perhaps to ensure an airtight seal for a volatile substance, or to create a perfectly level platform for a delicate instrument, or to allow 2 surfaces to mate with 0 leakage under pressure. It speaks of a culture that valued hidden perfection, an engineering standard where the quality you could not see was as important as the form you could. This relentless pursuit of the perfectly flat plane, the flawless joint, and the exact right angle reveals a mindset that saw construction as an act of pure geometry. But geometry alone does not hold a wall together. Once every stone was cut to perfection, the final, practical mystery becomes the stuff that filled the gaps, the ancient glue that turned separate blocks into a single, enduring mass. The pursuit of the perfect plane required a final, vital ingredient, something to bind flawless geometry into a single, unbreakable will. In ancient China, this binding force was not a simple glue, but a sophisticated science of organic and mineral-based adhesives, an 18th lost technique that turned everyday materials into eternal bonds. Here, master craftsmen developed complex recipes that served as the hidden sinew of their civilization, used for assembling war chariots, constructing soaring palace roofs, and sealing the tombs of emperors. These were not single-substance pastes, but engineered composite materials, carefully formulated from a pantry of natural resources. They blended organic compounds like durable tung oil, collagen-rich hide glue from animal skins, and sticky rice paste with mineral components such as slaked lime and volcanic ash. The result was a family of lacquers, mortars, and glues with properties that modern materials scientists are only now fully appreciating. One of the most famous and enduring examples is the sticky rice mortar, a formulation rediscovered through chemical analysis of structures like sections of the Great Wall and Ming Dynasty tombs. Researchers found that the ancient builders had mixed a standard lime mortar with a soup of sticky rice, a carbohydrate-rich variety of rice. When cooked, this rice releases amylopectin, a type of polysaccharide that acts as a natural biopolymer. Within the mortar, this organic component performs a kind of microscopic reinforcement. It fills the tiny pores and inhibits the growth of microcracks, creating a more compact, waterproof, and flexible matrix that is far more resistant to weathering and seismic stress than plain lime mortar. The tomb complex of Emperor Qin Shi Huang, guarded by his terracotta army, likely employed similar advanced adhesive technologies in its construction, helping to preserve its hidden chambers and structures against the pressures of time and earth. This represents a profound, applied knowledge of chemistry at the molecular level, an understanding of how to combine the strengthening qualities of minerals with the binding and plasticizing powers of organic materials to create something greater than the sum of their parts. It was a practical nanotechnology, using biological molecules to engineer the performance of inorganic stone and brick. This mastery of composite materials, of blending different substances to achieve a new, superior property, represents one of the highest forms of material wisdom. It demonstrates that the ultimate goal was not just to shape a material, but to transform its very nature, to create from the earth and the harvest a substance that could defy decay itself. This same transformative principle of taking a humble material and elevating it through knowledge finds its most breathtaking expression not in a glue or a mortar, but in an entire city carved from a single, living cliff. The same relentless pursuit of a perfect bond, achieved through chemistry in ancient China, finds its most radical expression in a theory that rewrites the very substance of the pyramids themselves. We return to Giza, but this time we are not looking at cut stone, we are looking at poured stone. This is the 19th technique, the Geopolymer casting theory, and it proposes that the Great Pyramid is not a stack of 2.3 million quarried blocks, but the world's most ambitious concrete project. The idea, championed by materials scientist Joseph Davidovits, suggests the builders possessed a lost technique of chemical synthesis, transforming the very landscape into a moldable building material. Instead of carving each multi-ton block from a distant quarry, the theory posits they crushed soft, local limestone, mixed it with a binder like natron, a naturally occurring salt, and water to create a slurry, a form of ancient geopolymer concrete. This slurry could then be poured into wooden molds directly on the rising pyramid course, setting quickly into a solid, limestone-like block. The evidence cited is compellingly subtle. Proponents point to the presence of fossilized air bubbles trapped within some blocks, a signature of a poured material, not a carved one. They note the discovery of organic fibers, perhaps from the mats or ropes used in the molds, encapsulated in the stone. They highlight the varied densities and mineral compositions found in blocks from the same pyramid, which would be more consistent with batches of cast material from different mixes than with stone from a single, uniform quarry layer. Most practically, this technique would elegantly solve the infamous logistical puzzles. Transporting a liquid slurry via buckets or channels is far simpler than moving a 15-ton block. Casting in place eliminates the need to lever and position impossibly heavy stones with perfect precision at great heights. The pyramid grows organically, course by course, like a layered cake. Traditional Egyptology, represented by many prominent archaeologists, offers a robust counterargument. They point to the discovery of ancient quarries with blocks partially extracted, matching the pyramid stone. They cite tool marks, transport roads, and the clear evidence of levering points on many megaliths. The consensus view holds that the immense, coordinated labor of cutting and moving stone remains the most plausible explanation, a testament to social organization rather than a lost chemical formula. So which narrative holds more weight? Does your mind see armies of workers hauling colossal blocks under the desert sun? Or does it see teams of ancient chemists mixing vast vats of liquid stone, building a mountain one pour at a time? The geopolymer theory, whether ultimately proven or not, forces a profound shift in perspective. It asks us to consider that the pyramid's true innovation may be invisible, a secret locked in the molecular structure of its stones. It suggests a level of applied chemistry that turns the pyramid from a feat of brute force into a feat of alchemical transformation. This final, speculative technique leads us to the ultimate, overarching mystery that has shadowed our entire journey. If knowledge this profound could be applied on such a scale, what cataclysm of time, conflict, or simple forgetting could cause it to vanish so completely from the human story? The final technique is not a tool or a formula, but a blueprint for a society. At Göbekli Tepe in Turkey, over 11,000 years ago, hunter-gatherers did something that rewrites the story of human ambition. They carved and erected a forest of immense T-shaped pillars from solid limestone, some weighing over 16 tons, each adorned with intricate reliefs of animals and abstract symbols. They did this before farming, before pottery, before the wheel, before any of the hallmarks we associate with settled civilization. The 20th lost technique, therefore, is the integrated knowledge system itself, the seamless fusion of social organization, symbolic planning, and practical engineering that made such a project not just possible, but a priority. This represents the ultimate lost knowledge, the silent architecture of a collective mind. How do you convince hundreds of people to dedicate years of their lives to quarrying, shaping, hauling, and raising multi-ton monuments when the daily struggle for food and shelter is a constant reality? The answer lies in a profound social technology, a shared belief system so powerful it could coordinate labor on a monumental scale. The intricate carvings were not mere decoration, they were a sacred language, a unifying mythology that provided the why. The practical engineering, the knowledge of leverage, rope making, and soil mechanics to erect these pillars in deep, circular enclosures provided the how. This site shatters the linear narrative that complex society must follow agriculture. Here, monument building came first. The temple may have been the catalyst for the city, not the other way around. Göbekli Tepe stands as a monumental question mark. It forces us to accept that advanced material knowledge, the ability to manipulate the physical world on a grand scale, can exist independently from what we traditionally define as civilization. It suggests that the human impulse to build meaning into the landscape, to encode our stories in stone, is a foundational drive, one that can mobilize a community long before it builds a granary. This is a holistic view of the past where spiritual vision and practical skill were two sides of the same carved pillar. The true loss is not the method for moving a single stone, but the social alchemy that turned a dispersed group of hunters into a unified force of builders. Their legacy is a silent challenge to our assumptions, proving that the seeds of greatness were planted not in fertile fields, but in a shared dream made manifest in rock. These silent teachers have left their lessons etched in stone and forged in metal, a scattered curriculum across the globe. We have journeyed from the interlocking stones of the Andes to the uncorroded iron of Delhi, uncovering 20 profound whispers from the past. These are far more than historical curiosities. They are testaments to a different kind of human potential, one that challenges the comforting story of a straight, ever-upward line of progress. The recurring themes are impossible to ignore: a relentless pursuit of precision that rivals our machines, a dedication to durability that puts our own planned obsolescence to shame, and a deep, almost intuitive, empirical understanding of the natural world. Our ancestors did not just use materials, they conversed with them, learning the language of stone, the personality of wood, and the hidden chemistry of earth and lime. They possessed insights born of patient observation over generations that we are still striving to decode with our microscopes and spectrometers. This journey reveals a history not of primitive steps, but of towering peaks of knowledge that were somehow lost in the valleys between. Perhaps the most vital lesson is not about how they built, but why their approach feels so urgent today. In an era of climate challenge and disposable construction, these lost techniques point toward a philosophy of resilience and harmony. The self-healing Roman concrete that grows stronger in seawater, the seismic dance of polygonal masonry, the smart plasters that clean the air, these are not archaic tricks. They are blueprints for a sustainable future, demonstrating how to build with the environment rather than against it, creating legacies that last for millennia, not decades. By studying these silent teachers, we might rediscover not just forgotten methods, but a forgotten mindset, one that valued longevity, elegance, and a profound respect for the materials at hand. So as the video ends, let the questions linger. Which of these 20 techniques did you find the most convincing, the most haunting, or the most inspiring for our own time? The conversation continues beyond this screen, in the comments below. Share your thoughts on which mystery speaks to you most powerfully, and subscribe for more journeys into the deep wonders of our shared past. The stones are still speaking if we are willing